bear with me while I get my stream set up, which it just does not seem to be wanting to cooperate tonight. Normally I'm a gamer and a musician. I worked on a keyboard a couple of nights ago and repaired that. I don't know if it works. Repaired a few keys. Tried to clean it, that sort of thing. So I'm letting that dry because I used contact cleaner, and that's going to be a few days. But until then, I have another project that I'm working on. And that project has to do with light. And it also has to do with noise. I'm still setting this up here. Bear with me. This is going to be a general, briefing, I guess you could say. It's more like the basics, if I could possibly go that far. But unfortunately, some of this stuff in the very beginning, it's a little bit more for the math, electronics, intuitive type person. But what I'll try to speak in English. I'm just going to give a quick, brief introduction to this website right here. And it's called World ITC, and they use various different types of electronics to speak to the dead. Well, this is what the site purports, of course. Outside of that, it's more like speaking or creating a situation where you're bridging the gap between reality and the next dimension, so on and so forth. You get the idea. The basic thing that started all of this was called ghost hunting, and they used these tape recorders to collect voices. I have done this before. It took me a few years and several months, even several years between times in order to fathom what was going on, or not. Basically, this will tell you, kind of what it's all about, so on and so forth. And, you can do tricks with cameras and voices. I'm not saying that any of this stuff is real. What I'm saying is that it's been done since like the 1950s or whatever. They call it instrumental transcommunication, so on and so forth. Yep. And there's a bunch of stuff in there, if you should be interested to check out that website. But wait a minute here. What's wrong? Something's not right. Okay. I'm on the wrong browser. That would help, wouldn't it? Let's try this again over here. Sorry about that. Okay, so this is the website. It's called World ITC. And it talks about what's called instrumental transcommunication. Yeah, it's a big word. And it seems as though over the last 10 to 20 years, they've come up with different names. There's various groups that's come up with, different kinds of interesting electronics to research all of this stuff. This website more or less kind of talks about a lot of the history that's happened since really the beginning of this, that they were doing all this stuff. Let me just recycle this web page over here because it doesn't seem to be working very well. So anyway, most of the basis for doing this type of stuff used magnetic tape recorders. Now, I've tried doing this with magnetic tape recorders, and it seems to work, fairly well. I've done it with digital tape recorders, and it don't work so well. So that's that story. Now, buried within this website, you have a small group of researchers. And if we click on researchers' results, it will talk about the various researchers that are on this list. Now, I'm not sure who maintains this site, but I would like to be on this webpage eventually, because the work that I do, this is what I do. This is what I have done. Let's put it that way. I don't want to get too off the thing here, but yeah, these are all the different researchers, and they've gone through different, they've done different tests. They have different equipment. Um, let's just say, in a nutshell, they do what they do. Now, I was very fortunate to actually meet one of these researchers. And this fellow's name was Erlen Babcock, and he was a technician like me, and he worked for a company in Massachusetts. And I discovered him through the website, and I thought, well, this guy's still alive. I need to go down and check him out, talk about things. I managed to actually get some of his equipment. I did not get any of his laser equipment, which was I was hoping, because he had passed away shortly, sometime after I saw him. And I went back down, and I knew that I could get some of his equipment and research. But all those research papers went to another site, AAVP or something, EAVP or whatever it is, voice phenomena, I forget, which doesn't really matter. And then the laser equipment went to his son, and I haven't really followed up on that, but he talks about him, what he's done. It talks about different stuff in here. It shows pictures of some of his tests that he was doing. It even has a diagram of what he was doing here, and I can explain it a little. So what he did was, his idea, it kind of sparked some ideas into my own head, because I consider myself an electronics expert. I know what I'm doing, and this stuff, dealing with the light, it was interesting enough for me to follow through with it. The reason I'll talk about shortly, hopefully. So he's got a laser beam, and the laser beam goes through a splitter. One of the beams goes through, and he's got a microscope objective here, and that bounces off a speaker, an 8-ohm speaker. I'll get to that in a minute. The other part of the beam goes through directly through, it does not bounce off the speaker, it goes through to the micro generator, whatever the thing he's got going on there. Now, and then he's got a tone generator vibrating the speaker. So the laser light comes onto the speaker, the tone generator is sending out a tone, it sounds like a wah, 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 like that. And I listen to it. I even have I have another one of his tapes, but I don't really feel so good. That's why I do strange things, just, I figured I'd get this project going on this internet, and that sort of thing. So, yeah, so one of the laser beams, maybe it acts as a reference, okay? And then the other one comes in, it's got the noise on it, and the two signals mix together, and so on and so forth. This fellow, he worked as a technician. He calibrated test equipment, and he was smart, okay? He was a pretty smart fellow, obviously, because he worked for, well-known companies. Unfortunately, I felt kind of bad for the guy. Once I learned what he was doing, and he really hadn't progressed in the laser light aspect of his research very much, because it's difficult. It's not something that you just throw together and make it work. Laser light is extremely sensitive, and if you get vibrations from a desk or walking around the house, you can just throw the experiment away. It's no good. It fails. So you got to have an almost perfect setup to do this. Um, I thought I was going to go that route, and the potential's there. So there's some other aspects of this happening. Um, there's interference patterns. There's noise. There's the laser light itself, and when I look at this, the thought just popped into my head because a thought popped into my head because I'm doing something with my own research that's very similar. So he's got a tone generator sending a tone into the speaker. Now, maybe the tone generator actually sweeps. I don't know exactly what his setup was here. It could be a sweeping thing. So, over like 15, 20 years ago, whatever, they come up with this guy, Frank Sumption, and was his name. He came up with this thing he called Ghost Box. And so what he did was he would take a radio and he'd take a generator and he'd sweep the frequencies of the radio really quick. I think it was up in the FM band or something. Or it could have been AM, who knows? It doesn't really matter. So he would have this frequency sweep back and forth across the band. And there was a claim that voices had come in and they would speak through this ghost box. They've sold it. Different people have marketed it. People have made money off of this. That kind of thing. Um, ploying on people's, preying on people's imaginations and beliefs, and basically just suckering them, making them believe that they're getting these voices off of this box. And they're random, and you can hardly tell what they're saying. Now, while it is true that maybe you get these weird, unexplainable voices that come through, there's really no consistency. And so, lo and behold, we have now the DRV, the direct receive voice phenomena, where the person makes a device and he's actually they're claiming that the spirits will speak directly through the device while he's talking. Well, it's a similar thing. This person has this thing set up on a computer, and he's got the thing going back and forth, the frequency thing and whatever. And, when I look at it, it's kind of sad. The guy is trying, okay? They're trying. But I don't believe that whatever he's doing is realistic. And the reason why I say that is because these influences on the noise are typically down in an extremely low voltage area. We're talking probably microvolts. And so what this person is listening to, he's got a headset on, he's listening to something that's like 500 millivolts of sound. Well, there's quite a difference between, say, 10 microvolts and 500 millivolts of sound. Your normal mixer, I'm a musician, so I know this, is usually like 1 volt RMS, 1 volt peak to peak or whatever. And, that's right up there. It's loud. So what you have to do is you've got to set up a system where you are extracting very low-level signals out of noise. Now, after, like back in the 50s and 60s and 70s, when they were working on all this stuff, all these researchers, they believed that the spirits and the entities were using noise as a basis for the communication. Well, you can't just have pure noise. You've got to have what's called interference. And I'll go through maybe a little bit of that business. So so anyway, he had this setup. Well, that's pretty cool. He was working with an idea. And how did he get this idea? Okay. I believe that people of this nature, including myself, are directed by beings and forces that are out there. And I think they're advanced alien intelligences, is what I think. not just people who have died, like Einstein. So there's a thing here. There's one of these researchers, I forget who it is, it's buried in here, where they had what's called time stream. And they used certain devices, and they would talk back and forth, and you could hear this voice. They call them technicians in the other dimension. And so the technicians in the other dimension are looking for technicians in this dimension to communicate with back and forth. Well, they had a setup. It was like this person was just talking like you'd hear him on a radio, like a ham radio, which I also happen to be a licensed amateur radio operator. And I do that kind of stuff. And so there was another fellow that he went outside, a little bit outside the ham band, and he claimed that he was getting voices from a place called Flatland. Okay, let me just pop that in there because it is kind of a curiosity. Flatland radio. Yeah, let's try that and see what comes up. It may not. Yeah, let me look. Let's go Flatland. Spirit radio. Now, most people wouldn't know this, you know. And it's probably really buried because it's so old. Wait, what's this? See what's happening here. Let's see. I don't know if I can find it. I'm not going to worry about it. So it was the discoverer claimed that he could talk just like an amateur radio or CB operator to these beings or spirits from this place called Flatland, and it was up around a 4 megahertz band. I'm assuming that he did not have an antenna connected. I'm assuming that it was just a communication. It was just he was talking to somebody. He heard these voices, and the voices were talking back to him. But the radio didn't have an antenna. Maybe it had a different kind of an antenna. It had a very strange type of antenna setup, and so on and so forth. That kind of thing. And the new radios, they go down to like 100, minus 100 dB. So let me just talk a little bit about what's called dB. It's called the decibel. And so we're going to go into the wiki. So the decibel is a measure of sound. 0 dB is pretty loud. Okay. Let's see if we can find a voltage relationship. I think it's this here. Where it says amplitude ratio, they're talking probably about voltage, is my guess. I'm not 100% sure, though. I'm just going to make an assumption. So let's say that it is voltage, okay? Amplitude's like a voltage. dB is a log curve. So maybe it will show the log curve. But anyway, when we say 100 or minus 100, okay, radios, the new radio technology today goes down to minus 106 dB. What that means is it's a very low level of noise, and you can pick up a signal. So if you send in a signal that's very small into the radio, you have what's called a signal-to-noise ratio. And that goes into the radio, and then you can hear whoever you're talking to. But you can see here, this is like, let's see, that's milli, that's micro. Micro is minus 6, nano is minus 9. We're talking like 0.1 nano. That's a power ratio. Yeah, that's. Oh, we got. What is this here? Micro, 10 microvolts. 10 microvolts. So, like I was saying, Now, let me continue here. Now, don't worry about the formulas, okay? Formulas are important, and I'm going to talk a little bit about that eventually. So, you can see here, there's a voltage, which is 20 log V out over V in, and it gives you a dB. The power is actually 10. It's 10 times. So on and so forth. I don't work with power. I work with voltage. So there's that. I'm wondering if there's a curve that they can show you by any chance. I don't want to. This is basically what I'm talking about. Is like a foundation type thing of sound level, noise type of thing. I don't see a curve in here. Let me see. Let's go back up here. dB log curve. Logarithms in decibels, mathematics of DFT. Let's see what that is here. I don't think it's going to show me anything. Okay, here's another thing. SPL. It's a sound pressure level is what that is. So that would be like experience of pain. There's a sound pressure level, and they use that to measure the sound out of speakers when you go to concerts and stuff like that. That is not a logarithmic curve. Yeah, I don't see it here. What the heck? Can I find one? Let me get rid of this wiki. Actually, could go to images. Roads, read audio charts, graphs, frequency, yada, yada, yada. Okay, this one, logarithm number. So here's a log curve. It's kind of over here, this black one. And it kind of goes up non-linearly. It doesn't go in a straight line. So that's a log curve. Now, as far as the dB curve, I don't think I'm going to find it in here. Anyway, we're not gonna talk about that. So so there's all these different ways to capture spirits from other dimensions, yada yada yada. And the basis, the foundation of all of this, the claim is that the spirits or the entities use noise as a basis for manipulating the noise in order to transcend the different dimensions. Now, first of all, think about it. Okay, first of all, there's got to be somebody, some entity or whatever in another dimension doing this. Number two, they got to know how to do it. Number three, they got to figure out where you are. Like, you know how big the world is. How's somebody from some spirit from some other dimension going to say, hey, this little dude down in this little place over here is sending out a signal? It's like me listening to my amateur radio and spanning all the band looking for somebody to talk to. There's a lot of communication going on, a lot of people talking. So you would have to come up with something that attracts them, something that when they look at the entire band at the same time, they see a blip, and they say, okay, that blip is interesting. Let's find out what it is. So that's my consensus idea of whatever. And most of the time, like in some of these experiments that I've done, I've been lucky. Anybody can do this. Anybody can take a small micro tape recorder, go somewhere where it's relatively quiet. Now, don't go to cemeteries. It doesn't work in cemeteries. They're all dead. I mean, really. You could go to places like something that was haunted, or some place that a hotel that was destroyed and something else was rebuilt over it. A place where there was a lot of people, a lot of activity in the past, A fort is a good place to get these sounds. But the way that you do this is you take this tape recorder and you be extremely quiet, set the tape recorder down. You don't want nobody else around, just you, nobody else. And so you ask questions, yada yada. This goes on for a half an hour or whatever. You try things in different places around the fort. Then you come home, and then you take the tape recorder and you listen to it and you send it on your computer. Now, computer, I mean, you've got filters and stuff like that. You can do so many things with the sounds, and you can extrapolate these voices out of this noise, and you're going to be like, now wait a minute. There's no way that this is a radio station, because a tape recorder is not a radio. It's a tape recorder. It has no way to pick up radio broadcasts unless you're right on top of a 10 kilowatt tower and it might bleed through, It's just not possible. I did one voice recording on a tape, and I was at my childhood home way back in the woods, way back. There was just nothing out there. And I did 2 hours worth of recording, and I brought it back, and let me tell you, there was all kinds of voices on that tape recorder, but I couldn't understand them. I could tell that there was something there that was not just noise. When you make a tape recording, and you're out somewhere, and there's nothing there, you don't expect to hear nothing on the tape recorder, right? I mean, there could be things inside the tape recorder that mix with other frequencies, and the mixture of those frequencies allows radio stations to come in, and you might hear bits and pieces of some radio station somewhere. So you have to account for the possibility that what you are hearing is not something from some other dimension. You need to be almost like 99.9% skeptical to do this, because if you're not, there is the potential that your own brain can manipulate the magnetic forces and create the very thing that you're trying to observe. And this supposedly is a known fact in physics now. If you are trying to observe something, it's very potential that you could actually create the very thing you're trying to observe. Yada, yada, yada. This is a physics thing. This is quantum. This is classical. It's wave theory. It's like all this crap put together with the potential that your brain can do this. Uri Geller supposedly he was one of the fellas that kind of did sort of things with pictures. He manipulated pictures and photographs on the old photographs and stuff. I believe that some of it was true. I believe that most of it was not. Maybe he was just a magician. Who knows? Who cares, right? The plain fact of the matter is, outside of all of what I'm doing here talking about, is that here we've got from the 1950s, we got 75 years of research in this. And where are we? You don't hear no big thing like some big discovery was made. You don't hear any of that. You just don't hear it. Because, why? Because it doesn't exist. Well, maybe it does exist. It just hasn't been discovered yet. So it's little old me, who most people would think I'm just an average, ordinary person, but I'm not. I believe my IQ is a little bit higher than most normal people. But then that IQ level doesn't maintain itself very well. Let's just say it kind of bounces around like a nonlinear equation. Sometimes it goes negative. But still, I have this ability. I believe that it's been my destiny in order to do something that the world is not ready for. And, just a little old me. And the chances of the right people finding out are only going to happen if I go out there and present myself. So that's not what I'm doing here. What I'm doing here is for a record of my research, and maybe it will spark someone's interest to continue it and whatever. and hit the right people. Maybe they'll send me $1 million and I'll get rich and take the money and go to Tahiti and disappear. Nope. Um, I'm losing my train of thought, ain't I? It's more like a confession, sort of. I've been wanting to do this for really over 10 years, but I've had a lot of personal things in my life that has prevented that from happening. I've had experiences that I cannot explain, and I believe that they are real. Let's put it that way. And so now I believe that I've been into electronics ever since I was like 10 years old. I got my ham radio license when I was 16, and I'm a little bit older than that now. Yep. I'm not going to tell you what my age is. You're just going to have to deal with that, and so on and so forth. So suffice it to say that I have a college degree. I also have been in the military, and I studied electronics in the military, which actually taught me more than what the college did. Hey, what can I say? Military is pretty good. So we're getting back to what we're talking about. We're talking about resistor noise. I don't even remember what the name of my stream is, to be honest with you. Oh, let me see. Where's my? Let me just take a peek here. Let's see. What is it? Off the cuff foundation. So what that means is, and we're talking about light. It says light. I'll get into that, but you got to talk about a basis for. Well, I'm working my way up there. So that's all of that stuff about World ITC and the building electronics things and mechanical things to talk to spirits from other dimensions, yada, yada, yada. So noise is a basis. Why is that? I think it's realistic to say that noise can be used to help create something. So if you take energy and you sweep the energy across a band of noise, it's possible that somewhere in that noise there's a signal, but you can't hear it unless you take another signal and sweep it across the signal that you're looking for. And so that's actually the basis of tuning a radio. Say if you want an AM station, 95.6 or whatever, you take the little dial and you dial it to 95.6, and lo and behold, you get a voice. And how that works, it's called AM amplitude modulation, frequency modulation, single sideband. There's different kinds of modulation. There's different kinds of communications. And they all use electronic formulas in order to extract the data. Aside from that, in order to, there's a theory that you have to have in order to extract the data, the smallest amount of signal that you need in order to extract useful information. That is called, well, I don't know why they call it Nyquist-Shannon. I have no idea. It's called the Nyquist theorem. And they got a bunch of garbage in here, which really, you have to have a signal that's twice the value of the signal that you're trying to look for to collect the least amount of information or something that's sort of useful. Maybe it's it's this frequency thing. It's got to be 2 times the frequency or something, and I don't know why there's so much crap in here. Let me go back to the Nyquist theorem. It states that a continuous time signal can be perfectly reconstructed from its samples if it is sampled at a rate greater than twice its highest frequency component. So let's say that you have a signal that's around 5 kilohertz, okay? And that 5 kilohertz signal is vibrating back and forth at some rate. Now, that rate could be, usually an audio rate is like, when I'm communicating, I'm creating an audio signal, which varies between, if I speak low, it's down around 500 hertz. If I speak high, it's around 10 kilohertz. that kind of thing. So usually like an average frequency is 1 kilohertz. So you've got to have something that vibrates twice that frequency in order to get enough samples to get the information of what the person is saying. Now, it's not just related to voice, it's related to any kind of communication. Morse code, teletype, ASCII, all those different kind of things. You've got to have this Nyquist theorem falls into place. So there's that. Okay, so then we're going to go back to resistor. We're going to go back to noise. So noise has a formula, and it has a temperature. It has a bandwidth of frequencies. It doesn't just have one frequency, but you could say that one frequency is only just one frequency. It's not noise. It's a signal. So if you've got a bunch of frequencies all mixed up together and they all bounce around and they're all random, you have this formula. It's 4k sub b times t times r times the change in frequency under the square root. Now, there's a constant involved, okay? That constant, evidently, it's called Boltzmann's constant. What I want to do, what my initial work is going to be, is I'm going to eventually get my notes out, and we're going to have my camera going. I'm going to write down, I'm going to do some work on some of my own theories live, off the cuff, and we're going to see if we can relate some of the constants and prove that some of the constants are not, they're not as accurate as we think they are, or that they don't work for certain frequencies or certain types of noise or certain types of temperatures, so on and so forth. Outside of that, we're going to make an assumption that most of the information that we have has been scientifically proven with experiments that I don't quite have the technology to use. So we're going to assume that some of these constants are fairly accurate and they have meaning. But the basic idea is that noise has a temperature. So if you take a resistor, let's say if you take a resistor and you put it across a battery terminal, and that resistor is a high value, like 10,000 ohms or something, it may not short the battery. Let's say the battery provides 1 milliamp, okay? And you've got a certain amount of resistor, and you've got this voltage drop across the resistor is going to be whatever the battery is because it's in parallel. So you've got this current going through the resistor, and the current is what causes the resistor to heat up. Now here it says here, experiment showed that thermal noise from a resistance of R with temperature T is band limited to a bandwidth of delta F, then its root mean squared, yada, VRMS, is this formula in general. So the voltage RMS is root mean square. There's a root mean square, there's an average, there's different types of voltage measurements. And so it's sort of like an average type of thing. It's not actually the average, but let's just call it an average. And so you've got this noise level, and if the current goes up, the noise level goes up, it's all proportional. There's a lot of this conversation that talks about proportionality, meaning if you have a fraction, the numerator if the numerator goes up, the function goes up. If the denominator goes down, the function goes up as well, I guess. If the denominator goes up, then the function goes down. All kinds of proportional stuff going on. Oh, it says right down here, thermal noise is proportional to absolute temperature. So some sensitive electronic equipment, such as radio, telescopes, receivers, are cooled temperatures to improve their signal-to-noise ratio. I was talking about that. You have a certain signal-to-noise ratio. that you got to have, and it follows this Nyquist theorem that you get all of these things come into play to collect this information. Most of the time, signals are pretty big, and and you can hear what's going on. There's some other things. They're talking about some other stuff in here, which honestly, it's like overkill, really. There's a curve here, which kind of looks interesting. So we've got this 4 kb TR. It's 4 times the Boltzmann constant times temperature, which is in Kelvin, times the resistance, right? And then it shows a bunch of frequencies. It says a noise power spectral density of an ideal resistor around room temperature. So you've got a room temperature, and you go from 0 hertz up to 1 terahertz. 1 gigahertz, it looks like that level is pretty stable. And then as it goes higher, the temperature goes down, probably because the resistor can only use a certain bandwidth of frequencies for whatever reason. Now, frequencies. So if we get my phone and we talk about light is in a nanometer range. Okay, so well, I could probably. Why is this? What am I doing here? Did I lose something? No, I guess I did. I must have just closed those out. If I go to, lost my train of thought. What the hell was I talking about? Oh yeah. If we go to, let's go to frequency chart. And we go to image. And you can see a bunch of stuff here, yada, yada, yada. We want one that's probably, maybe this one here. I don't know if you can see this. Okay, it doesn't really tell you. So you've got wavelengths on the bottom, frequencies on the top. Okay, so we've got radio. You get the audio frequencies away on the left, radio frequencies. I'm trying to get the megahertz number, but it's really hard to see. Damn it. I don't know what that number is. I think it's 10 to some power. It could be in like megahertz. I wonder if I can take a picture of that and see if I can find out what that number is. No, I don't have to take a picture. I can see it right here. 10 to the 10th power. 10 to the 11th to the 12th. So all those numbers are going up by a factor of 1. 19, 20, and so on and so forth. All right, so 10. All right, 10 to the 4th. 10 to the 3rd is 1,000. That's 1,000 hertz. So we've got 10,000 hertz, which is 10 kilohertz, 100 kilohertz, 1 megahertz is LF, 10 megahertz, 100 megahertz. God, I don't even know the numbers. You've got the microwave. Yeah, wait a minute. It's megahertz and then gigahertz, I think. Oh, shit, where was I? 10 kilohertz, 100 kilohertz, 1 megahertz, 10 megahertz, 100 megahertz. Yeah, 1 gigahertz. 1 gigahertz is 10 gigahertz, 100 gigahertz into the microwaves, 1 terahertz. I think it's 10 terahertz is infrared. 100 terahertz is it's into your light wave. I was just trying to relate frequency to nanometers, which is wavelength. Oh wait, they've got I wonder if that's in meters down there. It's just wavelengths. Yeah, I don't know. I know light wave is in the nanometer range. So if I go to infrared, that's -7, -8, or minus 9 is nanometer. Well, that's minus 8. Why does it go to minus 10? It jumps from 8 to minus 10. That stupid chart is wrong. I don't know. I mean, you get the idea. Okay, so if you look at this chart, you have frequency on the top, wavelengths on the bottom. Wavelengths are important. Wavelength is used in calculations, frequencies also used in calculations, but wavelength is more important because what that does is it tells you how big and small the wave is. Now, just basically, my theory is that particles and waves have a dual nature. Particles create waves, but waves do not create particles. Waves are a result of particle manipulation. You can't have a wave without particle. It's just, that's the way it goes. So you might ask yourself, okay, you got these antennas. And how do particles just jump off the antennas? Well, they do. I don't know. I think they do. Who knows? Because at the other end, you're picking up waves. You're not picking up particles. You got an antenna. Maybe the antenna is picking up the particles and making a wave out of it. Well, your antenna is built such that it resonates at the frequency you want to listen to. And in order for it to do that, it creates what's called a standing wave. And you have a piece of equipment in your ham radio shack that's called an SWR meter. And what that does is it measures the standing wave ratio. And what that is it's the amount of energy that is reflected back into the transmitted signal. So if that standing wave ratio is too high, your signal won't go out of the antenna. It will just fry your radio amplifier. So if the antenna is tuned to the correct frequency, it has a standing wave ratio of 1 to 1, which is it means that the antenna is resonant to the frequency that you're sending. Resonance is it's a thing. It's very important. That's just the thing. So as we go from the low end of the spectrum, the wavelengths get smaller and smaller and smaller and smaller. Now, we should ask ourselves, is this a linear or a nonlinear relationship? We could devise a formula and show you that, or we could just look it up because Google has everything, right? Is the relationship between the frequency and the change in wavelength as it goes higher, is it linear or nonlinear? Now, just looking at the chart, it looks like it's linear. It's a straight curve. As the frequency goes up, the wavelength goes down. Well, it just so happens that the frequency is related to wavelength by, I think it's by the speed of light. Let's see. So let's go frequency related to, we're getting a little bit away from the noise, but you got to kind of understand this stuff. Because this is the basis for I use science to do this project that I'm working on. I don't use this weird crap and just throw everything together and say something works and it's true. You can't do that. You got to have a basis. You got to have some scientific basis for a project of the scope of my nature, of what I'm doing, and so on and so forth. So there's a web page here. It talks about different things, yada, yada, yada. The electromagnetic spectrum. Every type of electromagnetic radiation, from radio waves to gamma waves, which is not true, obeys the velocity equals frequency times wavelength law, which is the same speed, the speed of light in a vacuum. Notice they said vacuum. What difference is frequency and therefore wavelength, yada, yada, yada. This single fact explains the entire electromagnetic spectrum. Unfortunately, when you get to higher wavelengths, higher frequencies and shorter wavelengths, I don't believe that's true. The particles they don't start acting like waves. It's been sort of scientifically proven, and I just sort of researched this out, was that light comes in the form of packets, or these. The higher up you go, the the change from the particle to the wave occurs in packets. I don't really understand, exactly what they're talking about, but that was the only way they could fit the equations in to solve the equations for all frequencies, is by considering a supposed fact that these things are all the particles are sent in packets, and so the fact of the matter is a certain percentage of those packets are going to get lost, but most of them, maybe 90% or 75% or whatever, they're going to formulate a wave. And so gamma and the gamma waves and cosmic particles and stuff like that, they're really, really high, very, very high frequencies. I don't know exactly what a relationship is as far as waves goes. I'm not really interested in that. My theory is working with light, because of this constant of light. It bothers the crap out of me. It's bothered me since the day I studied Einstein's theory of relativity when I was 16 years old. It's just been driving the crap out of me. Anyway, so they got frequency here. Radio waves, kilohertz to megahertz, microwaves, gigahertz, infrared, terahertz, visible light, 430 to 750 terahertz. Now, normally light waves are measured in meters, nanometers. It's more in the terms of wavelengths is used rather than frequency. Infrared is heat, remote controls for your TV and stuff. Microwaves, radar, cooking, Wi-Fi, radio waves, AM, FM, broadcasting, so on and so forth. Ultraviolet, nanometers, sterilization, sunburn, X-rays, medical imaging, gamma rays, cancer treatment, nuclear, so on and so forth. So if you have a particle that is, most of the particles are really small, and so they can go through material. If you have a certain type of material that's smaller, like a piece of metal or something, the particles can't go through it. They kind of have to be like translucent. So if you have a radio wave, let's say, down in an AM band, well, radio waves can go through anything except for maybe lead, okay? Because lead's really dense. So radio waves go through anything. Microwaves will go through anything. They're like these particles, they just go through solid material, because if you got this radio inside a house, how's the signal going to get there if it doesn't go through the wall, right? The wall, you can't see through the wall, but these lower frequencies can see through the wall. All right, so now you got infrared. You're getting into the infrared range. Here again, infrared cannot pass through the wall. However, over a long period of time, if you heated a wall long enough, then maybe the infrared signal could go from one point to the next. You can take your Streambo ad and shove it where the sun don't shine, and I'm going to take care of your business right now, because your crap is fucking stupid. I had Night TV is supposed to get rid of this freaking Steambo thing, and it never does. It used to work, It used to work, and now it doesn't work anymore. Don't ask me why. I don't know. I don't care. So then you get visible light. Well, visible light cannot go through a wall. So you've got a section that can't go through the wall. Then you go to ultraviolet. Again, you can't go through a wall. X-rays. Well, X-rays can go through most anything. Gamma rays, cosmic rays. These are particles that can go through the wall. So you've got a section of electromagnetic energy that cannot pass through a wall. It's called visible light. What if you could create a light frequency that could go through the wall? I don't think you can. So, which is interesting. So when I work with my project, I'm going to generate a frequency that's tunable, and that frequency is tunable within the radio wave, not microwave, because that's a little bit too dangerous. It's going to be audio, radio wave type frequencies, um, because they're more related to, you can take those frequencies, you can down convert them and create an audio signal. So, but the wavelength is very long, now that I think of it, huh? So maybe what I'm wanting to do is I can create an audio wave, convert the audio wave into the light wave. I can modulate, I mean, I could modulate a light wave and span the light wave, you know, like a tuner, like this ghost box thing, and do that very quick. And what I'm hoping for, or actually, no, I mean, my project is taking another light source of a single wavelength, passing it through back and forth, and looking for a signal that is an audio wave or radio wave. I'm looking for a signal that is smaller. The wavelength is actually larger. Uh, it's like tuning a radio but using light waves. Okay, enough of that BS. I don't even know why I get into that, because I really didn't want to get into that discussion. All right, so we've got this basic formula. We got light involved in a vacuum. You know, I do intend to use a bit of a vacuum in my project, but maybe that's counterintuitive, because I'm going to actually use something different. So we've got some information here that's connecting wave speed to energy. We've got Planck's constant. We got the different constants and so on and so forth. I don't want to get into that. I will say that the different colors in the light spectrum actually have a different velocity. How is that possible? If it's light, it's supposed to go, everything goes at the speed of light. Radio waves, microwaves, light waves, X-rays. Well, how is it that, you know, that's something that I sort of want to investigate. But let's see. Now they've got someone says here, the wave equation, which is really not the wave equation, V equals F lambda, I think that's frequency times wavelength, is the bridge between the classical wave picture, speed, frequency, wavelength, and the quantum picture, energy per photon. Now, that statement is extremely important, because that's the basis, that's the fundamental basis of the relationship between particles and waves. However, when they're talking about quantum, they're talking about photons. If an atom is activated in such a way that it releases energy in the form of a photon, and that photon has a certain spectral wavelength, and that's how they do the spectral analysis of the stars and stuff like that. You got chemical reactions happening, and those chemical reactions create energy level changes, and the energy level changes will emit photons or particles of light. Now, someone has said, I believe, that photons don't have any mass, they're just pure energy, so on and so forth. I'm not going to get into that. It is what it is. People can say whatever they want. My concern is relating the speed of light to the various colors and creating a sense of lights at a lower frequency, like infrared, will travel a little bit slower than the light at ultraviolet, which is a little bit higher. I read somewhere about the different colors having different velocities. And I'm going to just jump into that a little bit. I just wanted to talk about this formula because it's part of the explanation of particles and waves. So if I go in here and I say, let's see, different colors have different velocities. Enter. Oops. Something died. Why is DuckDuckGo just sitting there rotating? It died. That's why. Do colors differ in terms of speed, physics, stack? I don't know. Physics, stack, exchange. These are just people. Do photons slow down in different colors? The surprising truth. Why do different colors have different velocity in the same? That might be interesting. Let's see here. You've seen a rainbow. Yada, does red light travel faster than blue light? Or more does the speed of a photon depend on the color of its wavelength? Yada, 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 yada. In a vacuum, all photons, regardless of color, travel at exactly the same speed, which is the speed of light. This means red, green, yada, 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 yada. If you increase the wavelength, yada, yada, yada. But when light enters a medium, things get trickier. Here's where the light gets slowed down. Now I have to research this myself because I want to change the velocities of the colors. Like a prism is a medium, okay? So once photons hit a medium, they interact with the atoms and molecules. And I've discovered that if you have a crystal, what happens is the photons will actually align themselves to the crystal lattice, and they will, each photon uses a different part of the crystal lattice when it comes out the other end, which is kind of weird. This is something I just discovered. It's not the fact that they go through the slit. There's a slit, there's an opening, and then there's a crystal, then there's gratings and that kind of thing. But they do weird stuff. Anyway, let me see here. In glass, for instance, red and blue light refracts, bend differently because the refractive index, yada, yada, yada. This phenomenon is called dispersion, and it's why prisms split light into rainbows. But again, the photons themselves still want to move at the speed of light. It reveals that light travels more slowly in water, and it was one of the first experimental confirmations that light doesn't always move at the speed of light. C. Blue photons have shorter wavelength and higher frequencies, which means they are carrying more energy. I don't want to get into the topic of energy because it's a little bit away from, it's a little bit too mathematically oriented stuff that I just don't want to get into. So it's the medium has to do it. I know all colors have the speed of light, yada, 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 yada. It is not due to photon absorption or re-emissions, and that's why I hate the photon model. So many people misinterpret it, yada, yada, yada. Yeah, I really don't care about that conversation. I don't even know what that conversation is. So, well, let's get back to the noise thing. We talked about the Nyquist theorem, a certain amount of information. So we're back to this noise equation from a resistor. Now, let me just go through this. So V squared, well, if you take the square root, is a certain value there. While thermal noise has an almost constant power spectral density, a bandpass filter with a bandwidth passes only the shaded area, etc., etc. No particular practical filters don't have a brick wall cutoffs to the right and left edges. This is not true. It's supposed to be like filters usually have what's called a 3 dB bandwidth, where each side they drop off at a rate of 3 dB per decibel or whatever. Oh, I talk too much, huh? Thermal noise on capacitors is a resistor capacitive circuit. A filter, which is a low pass filter. This charge noise is the origin of the term KTC noise. Charge noise. Q is Q equals CV, which is the charge is the capacitance times the voltage over the charge. Independent of this is value, all the KTC noise arises in the resistor. Therefore, it would be incorrect to double count both a resistor's thermal noise and its associated KTC noise and the temperature that is known should be used. We don't have to deal with charge noise. There's reset noise, thermal noise on inductors, available noise power level. Signal power is often measured as a level with units dBm. Decibels related to 1 milliwatt. I prefer to use millivolt. At room temperature, 300 Kelvin, the available noise power can easily be approximated, and so on and so forth. Minus 173.8 dBm is called a noise floor. Remember I said the radios usually run around minus 106. You can get down to minus 173. That noise floor goes up as the frequency goes up. Minus 134 for an FM channel of a two-way radio. One megahertz, 2 megahertz. These are amateur radio. See, we're down to minus 106 here. Now they're deriving Nyquist derivation of ideal resistor noise. They're just deriving formulas, so on and so forth. Complex impedances, we don't need to get into that. Quantum effects at high frequencies or low temperatures. Without proper consideration, quantum effects which are relevant to very high frequencies or very low temperature in the absolute zero. The multiplication factor NF mentioned earlier is given by this formula. At very high frequencies, the frequency is equivalent to the value of K sub B T over H. Now I think that's the Boltzmann's constant times the temperature over the Planck constant. I don't know. See there, so now Planck's constant's jumping in here. But what happens is when you get up to the ultraviolet frequencies, there's some things that fail. Nyquist's formula is essentially the same as that derived by Planck for electromagnetic radiation of a black body in one dimension. Planck's law of black body radiation. In other words, a hot resistor will create electromagnetic waves on a transmission line just as a hot object will create electromagnetic waves in free space. That's all they're talking about. I'm going to reference black body radiation. this is sort of an important. This formula is related to a diode. I recognize this. Noise generator. Let's go to, I don't use diodes for noise generator because I don't think they're as random as they should be. They have everything has a bandwidth, but I don't see. Let's go back here. Let's see. Ideal model of a diode. This is an electronic component, by the way. I compare diode to solved examples. I'm looking for the formula. Yeah, I'm not going to find it here, am I? Okay, this is the current going through a diode, Shockley diode equation. I don't know what that V sub T is. I could be thinking of something else. E is there's a like natural logarithm. There's a logarithmic curve that happens when current goes through a diode. Some of them just switch on and off. T is the temperature in centigrade. Diodes have noise. Using the Shockley equation, small signal diode resistance of the diode can be derived about the same operating point, Q point, where the DC bias current is I sub Q and the Q point applied voltage, yada yada yada, small yada yada yada. This formula is equivalent to, yeah, I don't need this. Oh, wait a minute. That's a voltage at a certain temperature. The latter approximation assumes that the bias current is large enough so that the factor of 1 in the parentheses can be ignored. This approximation is accurate even at rather small voltages because the thermal voltage V sub T is equivalent to 25 millivolts at 300 degrees Kelvin, which is room temperature. So VQ over VT tends to be large, meaning that the exponential is very large. Let's just suffice it for the fact that, okay, what's this right here? Shockley diode equation has an exponential of V sub D divided by K, which is what is K? I don't know if I gotta go all the way to the top for that. Here's the equation right here I was looking for. This is current. K is not in that equation. K is a constant. I sort of like constants, but I hate them too at the same time. Oh, gosh. Diodes can be used to create noise, you know, so. What the hell is K? Diode modeling. It just pops up down here. Yeah, I don't know. I'm not that concerned about it. Anyway, I'm getting a little bit off the beaten path here, ain't I? See, we got quantum effects at high frequencies. Yeah. Relation to Planck's law, black body. Yeah, we just go to the Planck's law here. So here's this equation. This chart is extremely important. So this is a noise temperature chart. And the noise temperature actually fails. Something fails here in this ultraviolet region, which is on, I'm assuming it's on the right. Oh, it's on the left. It fails on the left here. There's some things that fail. I don't know why this is red, green, black. Classical theory is over here on the right. That's the temperature of visible light. Planck's law accurately describes black body radiation, shown here a family of curves of different temperatures. The classical black curve diverges from observed intensity at high frequency. We're not talking about intensity. We want to talk about temperature. Yeah, that's that curve. In physics, Planck's law describes the spectral density of electromagnetic radiation emitted by a black body in thermal equilibrium at a given temperature T, which is in Kelvin, when there is no net flow of matter or energy between the body and its environment. So there's a stable situation happening. See this exponent? This is this is one of the formulas for a certain temperature and a certain, I'm not sure what that V is. See, they've got Boltzmann's constant and Planck's constant related to each other in the blackbody equation. Here it says, and c is the speed of light in a medium, whether material or vacuum. So let me see here. So this first formula Well, maybe it only works in a vacuum or something. And this one relates to everything per unit wavelength instead of per unit of frequency. Okay, so V is velocity. Uh, B sub lambda must be spectral radiance. This form is not related to by the substitution of lambda equals C over V. These are different functions because the spectral radiance is defined in terms of equal amounts of radiation for each increment in the independent variable, and these increments are not the same in the two forms. The law may be expressed in other forms, such as the number of photons emitted at a certain wavelength, or the energy density in a volume of radiation. This is all related to noise, this is called a noise temperature curve. Higher temperatures, the amount of infrared radiation increases and can be felt as heat. And more visible radiation is emitted, so the body glows visibly red. At higher temperatures, the body is bright yellow, white, emits amounts of short wavelength ultraviolet. Planck radiation, the greatest amount of radiation that anybody at thermal equilibrium can emit from its surface with a chemical, etc., etc., etc. If the photon gas is not Planckian, the second law of thermodynamics guarantees that interactions between photons and other particles, or even at sufficiently high temperatures between the photons themselves, will cause the photon energy distribution to change and approach the Planck distribution. Distribution is called a statistical curve. There's different curves for different things. So that curve up there is a distribution curve, but it doesn't follow a normal statistical curve like a bell curve or something. It just weirded out in one direction. Now they're talking about power between unit solid angles. They're getting a little bit more particular into how much power comes out of some point in space, and they're putting all of that into the formula, which is not necessary for what I'm doing. I don't need to know that. I just measure the noise. I do something with the noise, and I expect a certain thing to happen. What's this picture here? Planck's solution is a freeze out of photon oscillator energies as hv, Planck's constant times velocity, divided by the Boltzmann's constant times the temperature, approaches infinity. average oscillator energy in units of kT. The Rayleigh average. There's another equation. It's called Rayleigh something I forget, and Compton wavelengths. Let's see here. We've got this, and we've got like I said, this is an off-the-cuff stream, and we're getting a little bit more in depth of what particles do to waves under certain circumstances. And before I jump into that, which is a little bit more complicated, let's get back to this chart. This means something. I mean, in terms of my project that I'm working on, this is where I was thinking that Planck's constant has a problem here. And they're using Planck's constant and the velocity as a means of, in different levels of this, whatever the heck's going on, in photon oscillator energies. And it follows this Planck average curve down towards the end over here. Yeah, let's just continue on here. It's going to talk about photons, and basically what I'm doing is I have a light source. I'm bouncing the light source off of diffraction gratings. I'm going to do something with the diffracted light, which I haven't discussed yet. I'm going to do something with it, create noise, run a light frequency in there like a radio tuner, and see if something happens. See if I get a signal, from some other universe. That's what it's all about. It's like, oh, this guy doesn't know what he's doing. You can think what you want. Though perfectly black materials do not exist in practice, a black surface can accurately be approximated. I don't need to get into derivatives. Stefan Boltzmann law. Those are integrals, double integrals. Spherical polar coordinates, we don't need to know any of that. The Stefan Boltzmann constant. Now, is that Planck's constant right there? Just out of curiosity. Radiative transfer. Einstein coefficients. Yada, yada. Spectral peaks is given by a certain formula, which honestly, we're down into the levels that numbers are so small. Didn't it show what this is? Black body at 5,770 degrees Kelvin. Stir radians is a measure of this angular output from a sphere. It's like this energy, probably ratio of solar flux above atmosphere to black body flux. Yeah, they're just doing a comparison of the curves, which I don't really need to know. You got photon gas. There's no gas involved in my experiments. what's involved in my experiments is actually going to be crystals. Because I want to control, I want to have more control over the photons. And so I'm devising an experimental setup to control photonic energy and make them stronger, I guess you could say. Make the photonic energy stronger in a sense that I can mix the photons together to create waves that otherwise would be impossible in the noise. Yeah, that's a mouthful, ain't it? Is derived from other known constants. K is the Boltzmann's constant. H is the Planck's constant, where h bar equals h divided by 2 pi, the reduced Planck's constant. And c is the speed of light. Well, if you're working with something that is in a medium, you can't assume the speed of light. C is going to be lower. So that means this Boltzmann's constant is going to be higher, assuming that C is equivalent to V, which is the velocity of the colors. I'm just throwing that out there for whatever it's worth, you know. So we talked about the frequency chart. We talked about wavelengths getting smaller at the higher end of the spectrum, which is ultraviolet, and the wavelengths are longer at the infrared area. The speed of light in a vacuum applies to all colors as long as there's no medium, but if there's a medium, such as a prism, the speed of light changes to what's called velocity. Velocity was back in that other equation that we looked at, which was V equals whatever the heck it was. So all of this stuff here, all these photons going into wherever they're going, are going to create a noise situation. And I am talking about this formula that has to do with temperature, noise temperature. Let me go back here. So if we look at V, which is the voltage, the RMS voltage squared, and you've got this Boltzmann constant in here. And you got a temperature, you've got the value of the resistor, and you've got this change of frequency here, delta F, as a frequency band. A bandwidth delta F. So you could, well, light doesn't go through a resistor, does it? Light is just photon energy, but it's going to create noise. I don't think you could make an assumption of putting light if you could change the delta F into the wavelength, which is in nanometers, and run all that stuff through there and come up with an equivalent value of noise. I don't think you could do it. I don't think you can do that. Ideal resistors. Okay, so this value, this RMS value has to be related to dB, which is decibels. Um, and I think, no, if I'm looking at nanometers, no, wherever that other chart was, that was a good chart back there that listed the frequencies and shit, the frequencies and something. I forget now. Around room temperature, a 3 kilo ohm, 3000 ohm provides almost 1 microvolt of RMS noise over 20 kilohertz. And 60 ohm hertz for R delta F corresponds to almost 1 nanovolt of RMS noise. 60 ohms hertz. This is 3,000 ohms. So the resistance is higher. So that means that the RMS noise obviously is going to be larger. They're saying 1 microvolt over 20 kilohertz. That's kind of the range of stuff that I'm dealing with. That's at room temperature. So one of the things is if you bring the temperature of the environment down, which is very possible, I could use a Peltier circuit with a piece of metal inside the test chamber and drop the temperature down. Then I'd have to do something with the humidity, and I can pull the humidity out using the vacuum setup. It doesn't have to be much, you know. I can monitor the temperature inside the chamber. I can monitor the humidity inside the chamber. I can create somewhat of a small vacuum type setup for the different colors that are going to exist inside the chamber. And I'm going to use lenses such that it will direct the color energy into these various crystals. Basically, they're samples. And I'm also going to direct the white light into 2 separate setups. One is for reference, the other is for the sample. And then I combine the two together into a comparator circuit to eliminate the fundamental, which is going to give me the audio signal that I'm looking for. So I'm going at, like, a laser is just, you know, maybe I can't use, I mean, I could use a laser. I think it'd be better just to grab an LED and try to fine tune it somehow. I got yellow, I got green, I got different colored LEDs. In other words, that's the way to change the frequency. Or what I do is I would take one of the diffractors and I would rotate. Maybe I could put the diffractor through a slit and then rotate the slit so that only one frequency of the diffractor comes out, meaning one color. That's what I need to do. But in order to get all of this stuff together, what I need to do is I need to convert the light energy into electrical energy. Uh, that's the project I'm working on. And it all has to do with combining noise. Um, I think it has to be a cold temperature so that the level of the noise is low. Because if the level of the noise is too high, this one here was talking about a microvolt. Of RMS noise, a 3 kilo ohm resistor. I'm going to copy this right here. Let's copy this. I've got a project notepad here somewhere. And this formula thing, I don't think I can copy. I think that's... Can I copy that? That's sort of copied. And then copy the web page. Like I said, off the cuff. What the hell? What the fuck is going on here? I can't copy this stupid web page. It's giving me freaking garbage when I copy it. Oh, you know why? It's got a dash in here. What the fuck? Why is this not... That is so weird. It's putting a whole bunch of symbols in here for that little dash. That's an underscore. Wait. Let's see here. Why the hell did they put that in there? Let's try this here. Oh, that's a dash. Wait a minute. Hang on. All right, I got it saved. So that's the web page. I'm just basically copying this for informational purposes, and it gave me some information about whatever I need to know. I kind of blurted out the whole project there, didn't I? I'm sure that none of that's really totally understandable, which don't bother me. I know what I'm doing. Noise, light. So you have what's called photo detector. Actually, wait a minute here. Photo detector tube. Photo detector. So I've got these tubes that I bought quite a while ago. Oh, they have these in CD-ROM drives. Visible in the photo in the center. Ooh. There's the little wires. Oh, he took this apart. That's the bare chip. There's three little blocks there. Maybe made of different material. Photodetector salvage from a CD-ROM drive. The detector contains 3 photodiodes. Oh, okay. So all of these common types include photodiodes, phototransistors, and photomultiplier tubes. They all have their own specific values. There's also solar cells. There's also this other thing that I forgot what the heck it's called. But the other thing that I'm thinking about, which I can't think of the name, it measures light intensity, but its response time is too slow. Response time meaning, like, if that thing would try to take the noise and read an audio signal off the noise, it couldn't do it because it's too slow. So you got to have something that can pick off audio frequencies that's the Nyquist thing. You got to have something that has a very high response rate. Now, I don't particularly need this photodetector tube. Although I have them, I'm not interested in measuring the levels of individual photons. What I'm interested in doing is creating an average. And it's telling me that because I'm using light waves that I'm supposed to make a picture of the average and use a CCD chip like I got for my telescope and put it on a timer, and then it will come up with a picture over a long period of time. Well, that's not what I'm trying to do. I'm trying to discover an audio signal from the light wave. And in order to do that, I've got to have a very sensitive, I think, photodiode that is able to go down into that range to pick off the difference in the frequencies, but difference frequencies are audio. So I'm not really 100% sure what I'm doing, but photomultiplier tube. But I got the idea, And here it talks about response to the output current divided by the total light falling upon the photodetector. Noise equivalent power, the amount of light power needed to generate a signal comparable in the size to the noise of the device. The square root of the detector area divided by the noise of the equivalent power. Gain, dark current. This is all charge coupled devices, CCDs, pictures. It does not talk about response time. I gotta go to work tomorrow, don't I? That's okay. I work later tomorrow. LEDs are which are reverse biased to act as photodiodes. See LED as a photodiode light sensor. But I'm actually, okay. Photoresistors, which change resistance according to light intensity. That's a photoresistor. The response time of those is way too slow for the purposes of my project. This is a good web page. I like this. I'm going to copy this web page down. Because this will give me the idea for detectors. Quantum dot photoconductors, which can handle wavelengths in the visible, quantum dot. Quantum dot photoconductors. Semiconductors, silicon drift detectors, X-ray, yada, yada. Photovoltaic solar cells also cannot be used because their response time is way too slow. Thermal detectors, thermopylae, photoreceptor cells, photochemicals. Rhodopsin photon-induced chemical cascade. Chemical detectors, photographic plates. Silver halide molecule is split into an atom of metallic silver and halogen atom. That's photography. Polarization is going to be used to, I use polarization. I'm not going to get into that. LED is a light sensor. Mobile phone. As a photodiode, LED is sensitive to wavelengths and equal and shorter, yada, yada. For example, a green LED is sensitive to blue light and some green light, but not yellow or red. This implementation of LEDs may be added to designs with only minor modifications in circuitry. An LED can be multiplexed in such a circuit such that it can be used for both light emission and... They don't tell you how, but what you do is you take the LED and you file the top of it off, and you can use it as a receiver. They don't tell you that. I learned that. So I don't know if this will tell me the response time. I got a bunch of these because I thought I was going to use these in my experiments. I mean, they could be used. Cadmium sulfide. Yeah, they don't tell you the response time. Specs. Quantum dots. Colloidal quantum dots irradiate with UV light. Differently sized quantum dots emit different colors. Quantum confinement. A quantum dot is illuminated by UV light. An electron in the quantum dot can be excited to a higher state of energy. Photoluminescence. Referred to as artificial atoms. Did I get my movie? My movie's not downloading. I did get one movie. Not particularly the one I wanted to watch. Quantum dots, optoelectric property. Oh, we're reading about quantum dots here. Single electron transistor solar cells, LEDs. Single photon sources. They're actually growing nano-sized particles to make circuits now. They're growing them on circuit boards using AI. It's crazy what they're doing. I mean, it's just so freaking crazy. Holy crap, there's a lot of stuff here. Gallium arsenide, quantum dots. Indium gallium arsenide quantum dot buried in gallium arsenide. That's like the fake atom. Particles containing cadmium, which are in batteries, have yet to be demonstrated in animal models after physiologically rather dosing. So on and so forth. Cadmium, selenium, zinc, sulfide nanocrystals. What the hell? Common QDs for batteries. Carbon quantum dots and graphite quantum dots are the main types of quantum dots used in batteries. QD-LED. Quantum dot light emitting diode. QLED. Quantum dots naturally produce monochromatic light, which is a light of one frequency. It's a which must be color filtered. QLED confers QLED. Yep. Anyhow, quantum dot display. 8K. Crazy, huh? Band gap energy. Uh, confinement energy. Semi-classical. Classical models electrostatic properties of electrons and quantum dots similar in nature to the Thomson problem of optimally distributing electrons in a unit sphere. I'm not worried about that. What is this? Physical insight. Surfactant molecules execute a random motion on the water-air interface. This motion can be thought of similar to the motion of ideal gas molecules. The Langmuir film states are classified according to. I was actually thinking of doing this soap bubble film on water. Because that's like a boundary. And it's a boundary between. Yeah, that's really interesting. Pressure, area, characteristics, yada, yada, yada. I'm going to type this in here. Let's see. Soap film on. I might have to do this on. Soap film Wikipedia. Organization of surfactants at both surfaces of the soap film. Daily experience shows that the soap bubble formation is not feasible with water or with any pure liquid. Actually, the presence of soap, which is composed at a molecular scale of surfactants, is necessary to stabilize the film, which means they are molecules with both hydrophobic and hydrophilic part. Thus, they are arranged preferentially at the air-water interface. Even in the presence of stabilizing surfactants, a soap film does not last forever. Water evaporates with time, depending on humidity. Moreover, as soon as the film is not perfectly horizontal, the liquid flows towards the bottom due to gravity, and the liquid accumulates at the bottom. At the top, the film thins and bursts. You can create. What if the film was in an oil instead of water? This is another area of noise that I kind of totally forgot about, and it's called chaos theory. It's recognizing patterns in the chaos, and these patterns are very susceptible to initial conditions. This is a perfect example of that. And it also provides what's called boundaries. And the existence of dimensions, other dimensions than in space and time, require that these, well, I don't even know why I said that, you have these boundaries. And so to get from point A to point B, well, it's physically impossible. You can't do it. So what happens is that something is created in one area of this film, let's say. It's like a butterfly effect. And somewhere else in this film, that information is picked up. How does it do that? It's knowledge. There's information. There's so much information in this picture right here. I mean, it's crazy. And in a picture like this, you could have the secret of the universe in one little area. You know, what causes this to happen? This is chaos theory. It's patterns in the, in the randomness of life and everything. It's cool. It's cool beans. I call it cool beans. That's a wicked picture. So I was wondering about actually if let's say here, if soap film is unstable, it ends up bursting. A hole is created somewhere in the film and opens very rapidly. Surface tension indeed leads to surface minimization, thus, due to film disappearance, the hole aperture is not instantaneous and is slowed by the liquid inertia. P is the liquid density. Okay, so if the density is high, V, which is the opening velocity, is low. H is the film thickness. So if I use an oil medium and put the soap film on top of the oil medium, I could use it as a source of randomness. It's noise. I'm creating a section of light noise, but it's just going to be like sitting there, unless it's going to dissipate. But if it's just sitting there, I could vibrate it with a transistor, an ultrasonic transistor I could put in there, which really wouldn't make any sense to do. Or, yeah, I could vibrate it with something that vibrates it at some frequency, or I could go through a wave of frequencies. That'd be a weird setup. I don't know why I'd want to do that. I was wondering what to do with them glass bowls. Actually, my setup is going to be small. Yeah, I've really gotten away from topic, is what I have. I've come up with, what's this here? Water drops on soap bubble films act like merging galaxies. That is sick. So you make a soap film and you drop a water droplet on top of it. What did they do? Did they drop 2 water droplets? Water drops on soap bubble films. That's some cool shit right there. This just came up here. This article was just written, like May 14th. That's like 10 days ago. I'm like right on the verge of technology with my project, and I'm coming up with ideas that that is sick. Look at that. Look at the simulation here. similarity. It's randomness. It's that they're just using a way to create a chaotic pattern. Uh, but my use, although it looks more video and picture versus audio, is information technology. Information. Isn't that crazy? Visual purple is a protein encoded by the erythroid gene, couple receptor, yeah. So I'm looking at things that create color naturally or as natural as possible, or creating noise color on a very random basis. Um, Whereas all I have right now is a spectrum of light. I want to create color noise is what I want to do. And this soap bubble thing. All right, so Compton wavelength has to do with the spectrum, the light spectrum, and so on. The inverse reduced Compton wavelength is a natural representation for mass on the quantum scale. Compton wavelengths for electrons, muons, and tau particle. Relationship to other constants, yada, yada, yada. A particle whose Compton wavelength meets its Schwarzschild radius has 1 Planck mass, spans 1 Planck length, and radiates 1 Planck energy. I'm talking about particles and their relationship to waves. And there's something else that I got to talk about too before I stop the stream. There's some formulas, interesting formulas in here. Modern physics no longer uses this form of the total energy. The energy momentum relation has proven more useful. De Broglie identified the velocity of a particle with the wave group velocity in free space. Relativistic momentum, and this is talking about an electron. Okay, so we're getting down to diffractions the slits where the light goes through. So a statistically large number of electrons, this is the double slit diffraction setup here. Light goes through, and these are particles, okay? And so when they go through these slits, the particles coalesce into certain areas, and those areas are defined by Fourier transform or the Compton wavelengths depending on the frequency of the photons. And there's a bunch of equations. They've calculated speeds and a bunch of stuff here. Wavelength, what's this? Allows the equations for devoted wavelength and frequency to be written as such. V is the velocity. This figure is the Lorentz factor, which I don't recognize. Lorentz transformation. Yeah. This is standing waves, resonance. I was talking about that earlier with antennas, yada, yada, yada. My refrigerator is talking. Various matter wavelengths. You get the mass of the particle, kinetic energy, wavelength. I don't know what PM is extremely small. Smaller than a net femtometer. Yeah, they're like really small. The factor h over mc in the equation is called the Compton wavelength. The unshifted wavelength is caused by X-rays scattered from the electrons that are tightly bound to the target atoms. Compton scattering. Okay, I got something else here. I've come up with some ideas just doing this, you know. So when you accumulate energy, accumulate light, wavelengths, whatever, depending on frequencies that you're using, those frequencies are added or subtracted, and they come up with something that looks like this, but that's not really a good picture. This might be a better one. You can't really see it that well, but if you have a signal that exists somewhere in time and space, and you want to get information from that signal, if there's any information on it, what you do is you mix it with another signal. And those two combined signals create what's called sum and difference frequencies. And you can get rid of the carrier frequency, and all you have left is the audio, which is left. It's called single sideband. This is what I'm going to be doing with the light waves. So let's see, if I just do SSB. Oh, image, yeah, it doesn't really. SSB, let's do it this way here. Single. So you've got something like this, maybe. This is kind of a good picture, I suppose. Of course, it would be smaller. You got upper sideband, lower sideband, and the carrier. So you have filters that filter out the sideband and the carrier, and all that's left is the upper sideband. Now, while this might be good for long wavelengths, for shorter wavelengths, you have to use a light filter. Easy enough, right? It just so happens that I have a book of light filters, and depending on where most of the energy resides, I'm going to be able to use those filters to mechanically amplify the information in that area, and then go from there and electronically amplify that information. It's a little bit complex, but it's a basic idea. So this would be a filter. It kind of drops. There's a band reject filter around 11 gigahertz. So that would take off the carrier at 11, and then the higher frequencies would kind of go up a little bit. But this is in the gigahertz range, okay? So you have a very narrow range in order to pick off an audio frequency. So the sensitivity of the light carrier, which is what my intention is, moving that light carrier across the band. If I use, let's say I use a micrometer that deals in micrometers, and I've got to go from micrometers to nanometers, it would take me so many turns of a micrometer to affect a linear turn of a nanometer to adjust anything that's coming off of that signal. Essentially, it would be like a small, very small type of a metric screw, maybe, with a little handle on it or something, and then attach that to a linear transformer, which is a mechanical, like a mechanical rod or something, to be able to move that back and forth with a mechanical ratio that reduces the micrometer down to nanometer movements. That's the difficulty in this. I hate mechanical crap. Hate it with a passion. But that's what I have to do here for my setup. Because I'm looking for, let's say, a 10 kilohertz signal. Let me see, where's my calculator? So if I change that to wavelength, how do I do that? It's the inverse. So you got a calculator. You got 1 divided by. All right. So I know that the 4 megahertz band is 80 meters. Okay. So if I do 1 divided by 4 million. That didn't work out very well, did it? 1 divided by 4. Wait, that's in meters, though. Its wavelength and velocity equals... oh, shit. Wait a minute. 80 meters. Hang on just a minute here. What the hell? Let's see. I just did that wrong. It's wavelength to frequency calculator. All right, you're just taking too long for my... all right, so if the wavelength is in meters and the wavelength... What the fuck is this bullshit? Oh, fucking God. Sorry about my cuss. Shouldn't be cussing. Wavelength, 80. All right, so it's 3.7 megahertz, all right? So I'm looking for, I want to convert I don't want to go the other way around. I act like I don't have to go to work tomorrow. I slept. God, I slept too much today. Damn it, get me off that stupid ass web page. No, not happening. Oh my God, the fucking numbers are not even typing in here. All right. So 10,000 hertz is what the fuck? 20, it's 30,000 meters. Yeah, this is not making any sense at all. What you're doing is you're taking the high frequency, you're mixing the high frequencies together, and you're coming up with sum and difference frequencies. But the question is how to be able to read wouldn't that be a proportion? The difference in something that's only 10 nanometers is not going to have enough bandwidth to come up with an audio wave. But you can modulate light waves. An optical modulator. Yeah, that's weird. All you got to do is just, you could take a LED and you could just mechanically couple it to a transmitter. You know, I mean, there's just, it seems to me it would be very easy to do, you know. That's weird, though. And then you take the receiver of the light, and then you retransform it down to audio. It's not what I want to do, though. I wonder if that's exactly what I'm doing. Uh, what is this here? Listen to a beam of light. This is like a little science experiment for eighth graders. Shall we listen? Oh, he said something about a paperclip and pushing turn on the voice amp and place the solar cell under a set of fluorescent lights. Many fluorescent lights flash at about 120 hertz, so you should hear a steady buzz from the speaker. Really? Alternatively, you can sign. Well, the stuff that comes out of the remote control has a signal on the infrared with the different buttons. I got a whole crap load of remote controls. I could use a remote control, set up an infrared electrical system to listen to the sounds that each of the things make on the infrared. Though I've never damaged digital player cell phone with this arrangement, there is a risk that DC to the headphone. Okay, some modern devices have segments. Yeah. If a small capacitor is wired in series with a paperclip, it will reduce the risk of so on and so forth. plug the mono plug to transmit in the headphone jack. Digital LED should light up. Turn the volume to just under the highest level. Play a song that can sit loud and set the player on repeat. Hold the solar cell from the LED and point it directly at the LED. Turn the voice amplifier so you should now be able to clearly hear the music from the player through the amplified speaker. So the cell the radio signal is going through the circuit and through this LED right here. The LED is pointed at the solar cell, which, by the way, has a very low response. And the solar cell is converting the energy to electrical back into the speaker. Now, I'm surprised he could do that. Because the fellow that, Erlen Babcock fellow that I talked to, said even the photovoltaic, the photo cells even have very low response. I thought about using a solar cell, but he said the response time is too slow. This is from an LED. So he's modulating an LED with the radio, which is kind of cool. You could use a test tone, whatever. So let's hear what this sounds like here. Oh, wait, what the hell is going on? I can't adjust the damn sound. Oh, boy. Wait, you can't hear this, can you? Wait just a second. Let me go to my settings. I might be able to change this back. Audio and speakers. Apply. Okay.
With its antenna is picking up electromagnetic waves in space and turning them into an electrical signal, an electrical current that's greater and less, and pushes a speaker cone in and out.
Yeah. Wow.
Turning the electrical signal into sound which you can hear.
I'm
just
in
like
sixth
this.
grade now.
When I plug in a headphone jack, it turns off the speaker in the radio, but that electrical signal is sent through the headphone wire.
Audio.
But I've sent it to a light-emitting diode instead of a headphone.
Okay.
And that signal, with more or less current encoding the sound, makes the light-emitting diode get brighter and dimmer. So I can take the light from the light-emitting diode and have it come across space and fall on a solar cell. Now, a solar cell turns light into an electrical signal. Brighter light into a greater electrical signal, more current, and dimmer light into a less current signal. Now, that electrical current can go through a wire to another speaker.
Now, this is something actually similar to what I'm doing. But the only difference is that in his situation here, which I'm finding it rather interesting, is that the energy, there's a lot of energy there coming out of the LED. The energy that I'm looking for is probably 100 times less than what he's doing. So the solar cell wouldn't be strong enough to pick off that energy. The LED, I think he said something about LEDs have a faster response time. That's what I was thinking of. Instead of using a solar cell, he could use another LED. In fact, if he used another LED of the exact same type, he would have a better response. You file the top of the LED off and use that as a receiver and an amplifier and a filter, and you could really, No, they also have what's called optocouplers, which have that built right into the transistor. Um, but that's yeah, that's taking yeah, it's taking electrical energy, converting it to some optical thing, and then taking it. It's got an optical receiver inside of it, and it takes it back and reconverts it back to electricity. I have some of those, and those things have a very, very fast response. They go up into the megahertz, which might be useful. What if the signal that I'm getting is a video signal, and a video signal has a special type of a waveform. I think it's 3.8 megahertz. Yeah, this is the signal right here. I don't know what I switched here. Okay, so you've got sync, you've got sync pulse, you've got a scan line, you get the back ports. I used to know all this stuff because I used to work. So you get a video signal here. The blanking signal. What is this frequency though? God, I can't remember. It's 3.58 megahertz, I think. All right, let me just go, let's do this here. Let's go 3.58 megahertz. Another thing you can do is you can convert sound into pictures. Yeah. Right here. The color section in the television receiver amplifies the 3.58 megahertz chroma channel, detects the modulation, and provides red, green, and blue video signals for the three guns of the tricolor picture tube. And I've got one of these too. So if we had something that had a response time that could pick off, say, 5 megahertz, there goes that frequency to whatever conversion thing. I don't know what it is. You know, it's in the microvolts. Solar cells, let's see here. Yeah, transient response. No, I'm a freaking robot. No, you're not going to have my cookies. They're mine. This is not going to give me what I need to know. It's electrical response time. Anyway, let's listen to this.
If I block the light completely, there's no light going across space, you can't hear the sound. If I let through a little bit of light, I get a quiet sound. If I block it totally, I get no sound at all. If I let it come through, it blasts away. Let's see how this works. So I have the electrical signal from the radio.
Yeah, okay, well, we don't need to get into that. That's, that fellow that I talked to said you couldn't use a solar cell. But that solar cell clearly worked. And I've got some. I got some of those. It seemed to work. Wow, that's crazy. That's like with no filtering, you know? It seemed like, yeah. So what I gotta do, I think for my first experiments, is that what I'm going to do is I'm going to set up LED circuits, receiver and transmitter, and I even have infrared receiver and transmitter LEDs, and I have to set them up. I gotta build those. I got some white LEDs, and connect those together and actually do some comparison tests with the photovoltaic cells and the photocells. And this Erlen Babcock fellow, he said he did all of that. I don't think he used solar cells. I mean, I just find that hard to believe that that solar cell could pick off that LED. Like the response time. I'm just, honestly, I'm blown away because I was told that you couldn't use it. So now he has a video right here saying that he's used it, so. Yeah, discussion of noise temperature. If we cool the environment, we can get a lower noise temperature. We can use a soap film to create a random colored environment. We can use actually, you know what? Let's do this right. Well, actually, I could do it here. Let's go to YouTube. And we want to look up no, we want to look up spectrometer. They've got some of these on the market now. They've got these little spectrometers you can get, which it's kind of crazy, huh?
This cute little thing is a fully functional optical spectrometer. Inside this deceptively small package lies some very interesting quantum technology and some very powerful algorithms. It costs about $50 here in China, but this product is about to be released on Amazon. We're going to test this device using lots of different light sources.
Introduction.
The first specified resolution of 5 nanometers.
Wow. The basic principle of how this device works is as follows. After the diffuser, light enters through a narrow optical slot and is directed at a reflective grating. Above the diffraction grating is the CMOS image sensor, which has patches of quantum dots deposited upon its surface.
Wow.
At this point, the wavelengths are quantized into 20 discrete bins, and this is where the magic of the spectral inversion algorithm starts working on the data.
The product has a mobile application for both Android and iOS, as well as a Windows PC application. They both work, but to be honest, they're both in need of some serious improvements. In their current form, the applications are pretty clunky with some very annoying issues. For example, the Windows application is not able to remember any of the settings, including which language to use or what COM port to connect with. You can't even adjust the window size or shape. But to be fair, these are small issues compared to my main gripe with the available applications. Whilst you can sort of export data, you can only export a PDF. Even though the software needed to export a CSV file could be done by a first-year software engineering student in about half a day. It wasn't included. So I asked the company why this was, and they made the shocking revelation that they deliberately do not enable that feature on their cheaper products. I'm almost lost for words to describe how that makes me feel as a customer.
Fortunately, I'm not. It's a complete and utter load of bollocks.
The LM2 device starts to outperform in terms of signal-to-noise ratio and dynamic range. However, the most important area where it has a major advantage over the Little Garden device is that it reports luminosity in absolute units, which are in terms of power per unit area. This has been calibrated to be better than 3% accurate over the usable spectrum of the product.
Wow.
Enough of the small talk, let's put this thing through its paces, and find out if this tiny spectrometer is actually useful.
We found these cool LEDs on Taobao. They come in these neat little glass bulbs and produce some intriguing colours. However, we do need to be cautious with the names of these colours, as Big Colour seems to have trademarked almost every possible name. So we have to be creative.
I've got one of those.
I mean, seriously? Cliff Walk is a colour?
Yep.
Big Colour is like an international conspiracy, planning world domination through lawyer-enabled colour squatting. Leading these chroma squatters is Axo Noble. Talk about a sinister company logo.
Our business is life itself.
Anyway, enough of that. Let's get on with testing some LED lights.
Oh, it's
This
a
particular
USB
shade of
thing.
red we're naming Man-Made Disaster. Apparently no one has trademarked that one yet. So over to you, Arthur.
One thing that all of these LEDs have in common is that the primary light source is a 450 nanometer LED. The visible color is completely controlled by the fluorescent coating that has been deposited on top of these blue LEDs. All of the yellow and red light is from secondary emissions of the mixture of fluorescent materials that are in the coating of a string of blue LEDs.
The second LED we are testing is called Daylight Smog. This light reminds me of the air quality in a city in West Africa that I used to visit. When I look at this light, I can almost taste the air again. Lovely. Anyway, let's see what Arthur has to say about this LED.
Thank you, Max. This is a classic white LED that has been optimized for a soft lighting effect. The fluorescent coatings have been mixed to produce a light that will reduce eye strain. And whilst it might have the color of Lagos smog, it is going to be far more relaxing on the eyes than other white LED options. The actual 450 nanometer LED emissions have been allowed to partially pass the coating to ensure that this LED has some level of whiteness.
For this next LED, Posh Arthur suggested the name Brothel Pink. I'm not sure how he knows about such things.
Sucking on my titty.
Okay, what the hell that
Glow
bullshit was? Huh?
There's a varying spectral output as it goes through its lengthy warm-up process. Initially, the majority of this rather interesting bulb is a high-pressure sodium lamp. For some reason, recently there have been a lot of videos on YouTube about this type of lamp, so I won't bore you with too many of the finer details. What I will say is that in the last spectrometer video, some people were wondering if this really was a high pressure lamp, as the spectrum looked too pure. Actually, this type of lamp has a varying spectral output as it goes through its lengthy warm-up process. Initially, the majority of the spectral energy is in the infrared range. This is to be expected as the tube is in the process of heating up the sodium metal to a vapour. In the sped up video of the lamp's startup process, the spectrometer constantly adjusts its sensitivity range due to the continuous increase in optical luminosity. However, this brightening is difficult to observe in the video because the camera is constantly compensating for these changes. I still find it fascinating how monochromatic light can destroy the perception of colour, even in the presence of other lighting. You can see at this point in the startup process that the double line at 589 nanometers is totally dominant. But as this high pressure sodium lamp starts to reach its normal working mode, some other visual spectral components will start to appear. There's also a strong near-infrared double line at about 819 nanometers. As the lamp reaches its working temperature, finally we see some of the other spectral components that are emitted by this lamp.
This spectrometer does not have the spectral resolution to see the sodium D double peak. That said, the little garden device can't resolve that either. As well as the doublet at 689 nanometers, there are a lot of the characteristic lines that are associated with high-pressure sodium lamps. This is a pretty well-known spectral fingerprint for this type of lamp. If we compare this result with the little garden output, we can see two major differences. For starters, the spectral resolution of the TLM2 device is not as good as the little garden spectrometer. The second noteworthy point is that the lower spectrum was captured before the lamp had fully warmed up, and so some of the minor lines are not present. It is also possible to see that the spectral accuracy is better on the TLM2. The little garden reports that the infrared peak is offset by 2 nanometers.
So there we have it, crystal to make the visible green beam. Here's a nice little trick you can do with a blue or violet laser. If you shine the laser beam onto a white LED, the fluorescent coating will be activated, even without any power being applied. Well, it impressed the kids anyway. And with this spectrometer, we can see that this secondary fluorescent emission is exactly as we would expect from this kind of LED.
Yeah, cute, huh?
Does is take white light within that chemical makeup. Sometimes you might have a coloured stone that doesn't yield an absorption spectra. Because of the design of it, I know pointy end to my eye, and then I would just bring everything up together, and then I can study the stone. Now you may be able to see it's very, very important when you're pushing light through these gemstones to make sure you get as much light going through them as possible. The stones really, really, really need to glow. If you don't have that glow, maybe light's escaping from the sides, it's going to make it more difficult for you to see that absorption spectra if it's there. So the other method we can use is the reflected method. So here I've got the gemstone on a nice dark non-reflecting background. In this case it's a little turntable which is attached to this stand which holds this large teaching diffraction grating spectroscope. If you don't have one of these, don't worry. A piece of material, just as long as it's dark, you can put the stone on the surface. In this particular case, for ease of demonstration, I've used a fiber optic light source, and you can see here that I've got the light coming in at about 45 degrees to the stone. It then bounces round inside and then back up out into the spectroscope. But you'll notice how richly that gem is glowing. So I know that the majority of light that's coming out of this fiber optic here is passing through the stone, and that is going to give me the best chance of a good result. So I've talked about the different ways of pushing light through a gemstone, but it's also really important to think about the type of lighting that you're using. So the lights that I'm using here are what we call a tungsten light. So they're a nice warm light. If I was to look at these lights, flashlight for example, just using the spectroscope, I would just see a nice linear range of colors. Some types of lighting, such as LED lighting, tend to have their own absorption spectra or absorption pattern. So you want to try and avoid using that type of lighting, purely because what you'll end up with is the absorption pattern of your light plus the absorption pattern of the gemstone, and you won't be able to work out what's going on. If I were to look through this spectroscope here, what I would see is a huge dark band covering all the colors except for red. This particular pattern is caused by the presence of an element called selenium. It absorbs every color except for red and just lets red through, so therefore we see red. In this particular instance, selenium is present, usually present in materials such as red glass. I will have done initial observation. First of all, I might see by example. The absorption spectra of a peridot sits well into the blue-violet. So if we use a spectroscope to push everything down to the red, we see.
So when she's talking about absorption spectrum, that means it's like a line. It goes down, it comes back up. It's like a filter. And so instead of seeing the lines of the color, we're seeing the absence of the lines of the color that's typical of the crystal that she's looking at.
We tend to see better into that area and get a. Okay, so I have here 3 very similar looking red gemstones, and I've been told that one of them is a ruby. Now, as a good gemologist, I've done pre-testing, so I've done observation, I've done polariscope, I've done refractive indices. The next, I'm going to move on to use the spectroscope. Now, having done previous testing, I think my most likely candidate for being a ruby is this little guy at the end here. But let's take a look through the spectroscope and check out. So I'm just going to give the stone a little bit of a cleanup. I've got my sticky tack on the end of the flashlight there, nice fresh batteries, so nice good glow. And I'm just going to take my stone and put him, nestle him in, bring the tack around so there's no white light escaping from the sides of the
Get all kinds
gem.
of oil on there,
so
you know?
we've got a nice glow there. And then take my diffraction grating spectroscope. Ideally, you need really nice darkened conditions. The darker the conditions you can have for testing in this manner is better, but obviously we've got the studio lights here, so hold the spectroscope up to my eye, bring the flashlight up, and as I look through, I'm seeing lots of little fine lines in the red end of the spectrum, fine dark lines, a whole cluster of them. I'm seeing a wider dark absorption band covering, or what would cover, the yellow-green. And then I'm also seeing some fine lines in the blue. In fact, also with this particular stone, I'm also seeing a bright orange line into the red. And we'll talk more about that in a moment. Here, knowing that we're looking for ruby, I know that the ruby spectra should have fine lines in the red, absorption band in the yellow-green, and fine lines in the blue. So I'm pretty sure that that is a ruby. So the important thing to remember is this, and other gem tests as well, for the most part, will not differentiate between natural and synthetic gem materials. So to get the most out of using your spectroscope when you're testing at home, first of all, you need nice darkened conditions. So try and work in a dark room, close the curtains.
Yeah. There's some homemade stuff out there.
Hey, it's Scott, and today we're going to take a look at the operation and functionality of the Seiconic C800 color meter. We're not going to go super. Let's do that really quick here. Any effect. The memory, measure, and power button, however, still do work. Of course, to unlock it, just hit that home button for a few seconds again. You'll see the icon change to that blue unlocked icon, and then you can go ahead and you can touch on screen to do whatever you want to do, as usual. So on this home screen, you have all the different types in comparison to the light that we just had set. So this is a continuous reading, and it's continuously comparing it to that value which you had previously set, which if you let go, it will return to on screen here. Finally, we have this little tool icon, and this will bring you into your toolbox, which if I had presets set, which I for that memory value. To back out of this, of course, just touch the little check mark next to the name, and it will turn that on and off. Next up is your CRI, and for example, if you want to customize this RA, which is your kind of average CRI value, you can tap that and you can display any of the specific values. So for example, R.
Holy God. See, this is what, yeah, almost $2,000 for this stupid thing? Seriously? I need to build one of these and make some money from it.
Light quality is something we don't often think about, but if you're into lighting design, a handful of parameters are visible. Despite advertising CSV exporting on their store page, the only available export format is PDF. Frustratingly, CSV export, along with many other features, do exist within the software, but are disabled for their lower cost spectrometers. The Android app, available on Torchbearer's website and the Google Play Store, suffers from the same limitations. Most of the features shown in the marketing images are missing, and like the PC software, the this feature causes the spectrometer to lock up and stop responding to commands. Quality measurements such as color rendering in. There are also a significant number of peaks in the infrared region, which don't correspond to error. Like the red laser, it has a spectral width of 7 nanometers. LEDs are relatively monochromatic and typically have a spectral width of around 20 nanometers. This UV LED emits at 399 nanometers. Despite being in the ultraviolet region, this wavelength is still easily visible to the human eye. Next up, we've got a 456 nanometer blue LED. While it emits a significant amount of light, to use the excellent color package in Python, which offers a great implementation of many color science algorithms. Examining sunlight, the calculated parameters are virtually identical. This consistency extends to other white light sources, with both the compact fluorescent and which provides use. Switching to the assembly view, we find it corresponds to a couple of SIMD instructions.
Material. And when it does that, it imparts additional energy into those atoms. This gets them all excited and they start bouncing around. Detectors that can detect, it seems kind of strange to just not put anything there. And of phone mess of wizardry and mirrors. Then there's this little plate on the top here. If we undo the 2 clasps that hold it on, it gives us access to where the object under test is going to go. And then if we walk around to the back and take off the plate back there, we can see there's another whole mess of mirrors down there. We're in the thick of it now. This thing is absolutely stunning to look at. It is also stunningly complex. Wow. There is so much going on. I mean, we have a full wire-wrapped backplane with 5 cards that are filled to the brim with ICs, implementing some pretty complex logic. And this mess of mirrors here is wildly complex. How on earth are we ever going to wrap our heads around how this thing works? Well, at the end of the day, it is still a spectrometer, so it's got to have some pretty basic fundamentals going on, and that is a light source, an object under test, and a detector. Our light sources are all right up here, the object under test goes in here, and the detector is right here on the front. So we have our foundation here. If we step through this thing one step at a time, we might be able to figure out exactly what's going on. Starting with the emission sources, we actually have 3 separate sources that cover a very wide range of electromagnetic radiation, from visible all the way to far infrared. And this little mirror right up here can rotate, selecting different sources. So you could put a single object in there and test it through multiple different sources by just changing out the detector. Now that mirror shoots the light straight down through this little 6-shot wheel here, and you can put different attenuators in there. It goes through an adjustable iris down here and shoots straight down into a different mirror, which reflects it back up into this very specially shaped mirror here that collimates it into a beam. This essentially takes all that electromagnetic radiation and smooths it out into a very uniform beam that it then shoots off towards this centerpiece here. And this is where the real magic happens, because this is a beam splitter. When that electromagnetic radiation hits this, half of it is reflected up into this tube, the other half passes straight through. Now in this tube and down here are 2 flat mirrors. The beams hit those, reflect straight back, and come right back into the beam splitter, where they are recombined and shot straight down out the bottom. Once those recombined beams come out the bottom, they hit this mirror here, which is a steering mirror that can send it to the left or right side, so you can have 2 different detectors. And then it does a little bouncing around and shoots right back out the front. It passes through this little window here. The object under test goes right here in the middle, passes through the object under test, and finally into the detector. And we can actually see everything that I just showed by looking in the brochure here. They have a wonderful little diagram in here that shows the total path of the beam coming out of our source. So you can see it goes through a source selection mirror, the filters, the iris, bounces off a transfer mirror into our collimator. From there it goes to the beam splitter. That's this like magical piece here in the center that splits it into, sends half to a fixed mirror, half to a moving mirror. That's the one up here in this tube. They reflect back, get recombined by the beam splitter, come down through an output beam selection mirror, off of a flat mirror to a focusing mirror, through the sample, which is going to be right here in the box, and finally to a detector focusing mirror and into the detector itself, which is right here on. It reflects through, it hits the beam splitter, and half of it passes straight through and hits this fixed mirror on the back. The other half of it, constructed, we can actually ascertain a whole lot more information about the end of that finalized waveform that ultimately we detected using our detector on the front. And in use today, the computer has long since been retired and replaced with far more modern stuff. But I'm a bit of a fan of old PDP-11s, and Mike wanted to see those 11s go to a good home, so he hooked me up with a bunch of parts that just so happened to be absolutely everything necessary to get a PDP-1173 hooked up to a BOMIM DA3. In this admittedly unconventional case, there is a PDP-1173, 2 megabytes of memory, a BOMIM DEB41 paired with a Matrox QRGB that give us the full color graphic capabilities, the BOMIM DEB18 that interfaces with the vector processor board, and an 8-inch floppy controller, as well as a Winchester drive controller. On the front here, we have our 70 megabyte Winchester drive and our 8-inch floppy drive. And then on this side here, we have the high performance vector processor. Once we're fully booted up into the operating system, it's just a pretty standard RSX11M install. We can type hello. It's gonna ask me for my account or username. It's gonna be Usagi. The password is Usagi. And there we go. We can do like a directory listing here, which there's a lot of stuff on this drive, so it's going to take it a second to list it up to it. So connected to it. Make sure that everything is kind of doing what we expect. Next episode, where we're going to dig into this thing and try to get some electrons flowing through it. So I hope you guys.
Yeah, good luck with that.
Light quality is something we don't often.
This is basically like, somewhat of the setup that I'm doing. It's a little bit more, the idea of switching different light sources look pretty cool. What's this setup here? That was different.
The ability to say what any chemical is. So for example, if we put some of this in here, The chemical formula for this is C6H5N3. And if we put this through the mass spectrometer, it would tell us that we have ratios of carbon, hydrogen, and nitrogen with a few other assumptions. And then we would know, oh, if we ever see that ratio of carbon, hydrogen, and nitrogen, we know it's benzotriazole. Boom, there you go. So it's a way to give us an instant readout of what a chemical is just based on having access to a little bit of that chemical and no other information. But you can see there's a pretty big problem here, right? If we take another chemical that has a similar formula, this one is C10H8N2, you'd say, okay, we know that ratio, we could identify this. But what if we had a mixture of both of these? Now we've got a problem because all the carbons mixed together with all the hydrogens and all the nitrogens, and we would have some new, well, this is terrible for vacuum because the rubber is not going to be compatible with this. Through the stopper, and I've got a little lead here so I can quickly disconnect this and then open this up. And the way it's built is basically taking a rubber stopper and loading up some needles, some long sewing needles into a drill press and then shoving them through the stopper and then soldering some bits to this end of the needle. So basically we get a pass-through. It's really the cheapest, easiest way to make a vacuum pass-through. And at first you might be thinking, well, this is terrible for vacuum because the rubber is not going to be compatible with this high-end vacuum system. Well, first of all, this is not a high-end vacuum system. And second, you might be surprised, actually, the record, even with all this rubber exposed on the inside of my vacuum system, we can still get this down to really good vacuum levels. And that ended up not being a problem, thankfully. Quick note about the vacuum system. You need really good vacuum when you're doing mass spectrometry because the ions are moving relatively slowly through here. So there's a lot of time for them to be interfered with by, gas molecules that you don't want in there. Ideally, you want literally nothing between the collector and the emitter, but nothing is an impossibility. So we try to do the best we can. So this is just a Penning gauge, a vacuum gauge to see how good the vacuum is in there. And this is a turbomolecular pump. Which is really convenient for this because we have to start it up and shut it down very frequently. And this is one of the fastest start and stop, vacuum pumps you can get, and it's also very clean.
Like I'm going to use a turbomolecular
so the basic idea is just put everything together, turn on the roughing pump on the floor there, and then turn on the turbomolecular pump, and the whole thing gets down to vacuum in about 10 or 15 minutes. And when I say down to vacuum, this thing will typically achieve 5 times 10 to the minus 4 torr, which is pretty good considering there's rubber stoppers and everything in there.
You need a vacuum.
Everyone is concerned about leaded, solder, copper problems and everything, but we're way beyond that. Like if we have large rubber stoppers exposed, that's going to be a much bigger issue than leaded copper or leaded solder and everything. I made this copper tube contraption on the lathe and originally just used rubber tube fittings to connect the thing to the various vacuum pumps, like little bits of rubber tubing like this. This was a super big mistake. So this PVC tubing outgasses like a beast. In fact, I almost didn't believe how bad it was. Like even using a little section like this, just a couple centimeters exposed in there, totally unacceptable. It ruins the vacuum. I don't know why those black stoppers are okay and this isn't, but it isn't okay. And then I used this, professional rubber vacuum hose, and this was also pretty bad. Again, I don't know why this is so much worse than those black rubber stoppers, but it was. It might have just been the fact that using a hose clamp with these vacuums is just a really bad idea. But again, I'm using black rubber stoppers here, and it's fine. So anyway, I ended up brazing on some custom KF fittings on the ends of this copper tube, and that's how I put everything together. Water that contains our sample dissolved in it right on the filament and let it dry, either by passing a current through the filament or just blowing some hot air on it or just waiting around. And eventually what we'll have is a filament that is coated with the powder, basically. It's just a way of getting the powder onto the filament. And then we put this thing together into the mass spectrometer and turn it on and heat it up. And when the filament gets to, red heat, it will actually ionize the sample for us. It's actually a process that happens all by itself. Like you've heard of tungsten filaments boiling off electrons when it gets hot. It can also produce ions and solder everything together so that the solder holds everything and things really get interesting. But anyway, back to this ion. So we put these other 2 electrodes in here. It's actually a brass plate, one on each side, and they're electrically isolated too. And the idea there is that we can apply a little bit of voltage to these brass plates to kind of steer the beam in a way that we want to happen, right? So if you're but it is very high gain. And the trick here is that the amplifier has to be really close to the source because the input capacitance is a big problem. And this was actually an oversight that I missed for longer than I should have. But if you have input capacitance, that really ruins your whole transimpedance amplifier. So you want this thing to be as close as possible and as little input capacitance as possible. And in this case, this whole thing is maybe on the order of, I don't know, 10 puff or something like that. And that's even that is getting to be kind of a problem. But we'll talk about the usage also a little bit later.
Break.
The power supply for the preamplifier is just two 9-volt batteries. And conveniently, I've got some voltage regulators here. Conveniently, these batteries are nice because you get a bipolar supply and it's super low noise and it's isolated from everything. It's actually a really nice way to do a front end like this. And then the output from this million gain transimpedance amplifier goes to this cable and then over to the bench, and we'll talk about that next. This is the cable from the preamplifier going into this low-pass filter, and then we also apply another 40 dB of gain, so another times 100. So the total gain here is 100 million, and then the output from this filter goes into the scope.
Oh my God.
The scope is configured in XY mode, so the vertical component of the trace is coming from weaker magnetic fields. And this is a totally valid way to do it too. But the problem with that is we need a huge electromagnet and we need to control it very carefully. We might have problems with hysteresis and so on. So there's actually another trick. Let's take a look at the schematic and we can see what we're going to do instead. Instead of changing the magnetic field strength, which would kind of be equivalent to rotating the prism in a light-based spectrometer, what we're going to do instead is change the incoming ion beam speed. We're basically going to be changing the acceleration voltage back and forth. And I know we're kind of pushing the analogy far here, but this is sort of equivalent to redshifting the entire beam of light that we're sending into our prism. So if we were to redshift all of the light going into our prism by a known amount, that would indeed shift the output spectrum. And if we knew what that shift was, then we would be able to figure out, what we're doing. Right? Like the ions are jumping. This thing works, protons and 6 neutrons. That. And we know what the fundamental charge is. Numbers a little bit. How asymmetric this peak is, right? There it is, 0.6 down. That is actually the isotope of potassium sitting there. And then it gets even better. If you look at the Dewdney papers and the Scientific American papers, their peaks are really asymmetric too. So I am almost certain that the isotope is hiding in there. And the
Yeah, brother. Yeah, that's interesting stuff. This is what I gotta build. I gotta build a spectrometer, a decent one. I want the ability to have a vacuum, but I don't need that kind of crap. What's this? This dude's got an FTIR spectrometer. It's funny. From what I'm seeing with the spectrometer stuff, they're not really getting into like you turn the spectrometer in such a way that you're looking at the different colors. I don't see that happening here. What's this?
Here's how a spectrophotometer works. A lamp provides the source of light. The beam of light strikes the diffraction grating, which works like a prism and separates the light into its component wavelengths. The grating is rotated so that only a specific wavelength of light reaches the exit slit.
Right there. That's what I'm talking about. So they've got a slit going from the light source onto the grating, and the grating reflects back through another slit. The grating is rotated so that so this slit right here, I mean, I got some razor blades that I can make a mechanical slit to attempt to do that. But that would be rather difficult. I thought they used something different. I must be missing something.
Then the light interacts with the sample. From this point, the detector measures the transmittance and absorbance of the sample. Transmittance refers to the amount of light that passes completely through the sample and strikes the detector. Absorbance is a measurement of light that is absorbed by the sample. The detector senses the light being transmitted through the sample.
At any rate, I went a little bit off tangent. I don't know why. It's just what I do. Yep. Noise. The world is full of it. And there's so much cool information that can be gleaned from noise with the toys. Yeah, I'm done. The story of my life.